Okay, so at the top of section 1.5 is talking about a first day demonstration. This is something that I showed most of you last year or 2 years ago, so you've got a good idea of what happened. But I'm going to write down the things about it, and I'll remind us if we've forgotten. So we've got what happens before the reaction, what happens after the reaction in terms of observations and actual chemical substances. There's a table here. This reaction, if you think back to the very first day of school a year or two ago, I had a small beaker full of nitric acid, and so let me draw a beaker for us. Something like this. Had a very small amount of a colorless liquid. It was clear, we could see through it. This was nitric acid. Nitric acid, clear, colorless liquid. Just as a reminder on these two terms, common usage, these two are the same thing, but in the chemistry world, clear is a measure of how well can we see through it, and colorless would be the actual color. And we are adding a penny to it. So we've got a penny, and this is copper to brown solid. As far as the actual chemicals go, we have copper, solid, nitric acid. Does anybody have another formula for nitric acid? We will soon. And something, yeah, it's a good guess. HNO3 aqueous. Later in the acids and bases unit, we will memorize the strong acids and strong bases. There's only about 7 of each of them, and they follow a pattern, so they're relatively easy. These are my two reactants, copper and HNO3 nitric acid. Afterwards, what we have is, here's a beaker, and during the reaction we had lots of bubbling, there was color changes, there was gases being produced. The solution is now a pretty dark blue color. There was a reddish brown gas that kind of flowed over. So we'll write these down. Red-brown gas. If you ever get a face full of it, it's really hard on your lungs, really hard on your throat. Another observation that none of you were able to make at this time a while back was that this beaker got really hot. If you were holding it, just had it sitting in the palm of your hand, I don't know that it would have burned you, but it definitely feels hot to the touch, like a mug full of fresh coffee, about that hot. The chemicals here, we're talking about copper 2+, which is aqueous in the solution, and NO2 gas. What's that? So just based off of what we have right here, let's figure out what element is oxidized, what element is reduced, if we have enough information. So oxidized. First question, what happens to an element when it is oxidized? Something with the electrons. Maybe take a look back at the mnemonic that you have. There were two of them. Yeah. Oxidized, we are talking about lose electrons. Electrons have a negative charge, so if we were taking them away, something would become more positive. So we're looking at the copper here. It's neutral, and then it's more positive over here because it lost 2 electrons. So copper, its original oxidation number here is 0 because it's a neutral element. Here its oxidation state is +2, which is the charge of its ion. Copper, 0 to +2. So with that, now let's figure out which one is reduced, which would be gain electrons. Any reaction that is redox has to have an oxidation half, it has to have a reduction half. If it has one, it has the other. Without both, it's not even a possibility. So let's look at which one is reduced. So first off, we have hydrogen, nitrogen, oxygen as choices here. Over here we have nitrogen and oxygen. Oxygen pretty much always has the same charge or oxidation state. Which is -2. Same thing over here, -2. Hydrogen's +1. Can anybody tell me the oxidation state of nitrogen and nitric acid? +5. So this is a neutral compound, and we want to make sure that everything totals up to 0. We had +1, we had nitrogen, which was our question mark, and we had 3 oxygens, which was -6. So in order to make everything equal 0, it was nitrogen. That's how we got the +5. What's the oxidation state of nitrogen in the products? Everybody think about it for a second. This is a neutral compound, so everything should equal 0. +4. So here's what we have, +5 to +4. It's becoming a little more negative, which means it's gaining electrons. +5 to +4. In the next line, it talks about the oxidizing agent and the reducing agent. This is a little bit weird, and I'm not sure that the AP exam actually asks you this question anymore because it was just a little more confusing. So what happens is whatever compound had the element that was reduced is the oxidizing agent. It's the opposite. So HNO3, where you see the blank, is the oxidizing agent. And I would recommend spending 90% of your brain power here and only maybe 10% here. And then copper is the reducing agent. because it was oxidized. Let's not overthink this too much. Really, the important stuff is here. There's an interesting relationship in the lab I've been contemplating, which is one reason I didn't set up your demonstration here. So you can figure out how much copper is in an alloy or a mixed up sample by doing this reaction. So for instance, they can do it with brass bullet shell casings. So different brands have different brass compositions. It's made up of copper and zinc. And what you can do is put the shell casing into some nitric acid. This reaction happens. And there's really two products. There's some sort of a zinc in the solution, which is colorless, and there's copper in the solution, which is blue. And then, so it's just a matter of figuring out how much copper is in the solution and working backwards. Does this sound familiar? Is there a way we could measure the amount of copper in a solution? And based on the fact that we know it's blue, we could stick it in our colorimeter. We could figure out the actual concentration of the copper and use that to work backwards to figure out the actual percentage of copper. And this is a legitimate lab test to figure out what shell casing is this, what brand is it. Anyway, I thought that might be a lab worth trying. Balancing the redox reaction using the half reaction method. Everybody here knows how to balance a chemical equation. Redox is a little bit different. Like I mentioned before I started the video, you have to take electrons into account as well. The electrons have to be balanced. In a redox reaction, the amount of electrons lost in the oxidation process must be equal to the amount of electrons gained in the reduction process. In a chemical equation, not only do atoms of each element need to be balanced, but also the electrons transferred need to be equal. So there's a method to balancing these. Number one, assign oxidation states to each element. Figure out which element is oxidized and which one is reduced. That's going to be important for us. We're going to treat these like two chemical reactions. One equation is the oxidation half reaction, we call it, and the other one is the reduction half reaction. You balance the half reactions first before we put them together. So a quick preview, it'll be easier once we've seen some examples though, like always. Balance the half reactions. So in a non-aqueous reaction, balance the charges with electrons. In an aqueous reaction, balance the elements that are not hydrogen, not oxygen. Balance everything else. Then you can balance oxygen by adding water, and then you can balance the hydrogen and the water by adding H plus hydrogen ions. Both of those two things exist in water. Both of them are present in an aqueous solution. Then balance the charges with electrons, and we'll skip that last one. Number 4, make sure the electrons lost in oxidation is equal to electrons gained in reduction. Then add the half reactions together. This is something that's a little easier done than described. So go ahead and flip to the back. The first example, we have solid aluminum plus copper ions, aqueous, yields solid copper plus aluminum ions, which are aqueous. So number 1 says assign oxidation stage to each element. So let's go along and write these in. Aluminum, solid, this is an element. It is neutral, and its oxidation number is 0. With an ion, it's the charge of the ion. So copper is +2. Copper in the products is neutral in its elemental form. It's 0. And then aluminum, same as its charge, its oxidation state is +3. Identify which element is oxidized, which element is reduced. Remember, losing electrons is oxidation. Which one of these is losing electrons? Here's what it looks like. Losing electrons would make our charge more positive. And so we have aluminum with 0 becoming +3 because it lost electrons. Reduction, gaining electrons, its oxidation state would be more negative, +2 to 0. There's your copper. Number 2, write the oxidation and reduction half reactions. So let's start with our oxidation. And we're just going to break this in half. We're going to leave a little extra space. So oxidation, we said, was aluminum. We have solid aluminum becoming aluminum ions. This is the half reaction as far as taking it from the full chemical equation. We also have electrons being lost. So here's what happens. We have a neutral aluminum with all of its electrons, and it becomes the aluminum ion, and 3 electrons went off somewhere else. So we had a neutral aluminum, and it became an ion plus 3 electrons somewhere else. Our reduction half reaction, we have copper 2+ becoming solid copper. It's gaining electrons. So the copper ion plus electrons are making this. When you're gaining, we're going to put them over here. And the charge was +2 to 0. You need to have 2 electrons here. These are our 2 half reactions, and they are balanced in terms of atoms, and they're balanced in terms of electrons. So for step 3, we were able to skip a bunch of things. Number 4, make sure the electrons lost in oxidation is equal to electrons gained in reduction. This is step 4. Make sure that, do this for us again. Make sure the electrons lost in oxidation is equal to the number of electrons gained in reduction. They're not the same. So we have to do these common multiple. Here's how we do it. Everything in this reaction is times 2. Everything in this reaction is times 3. Times 2 here gives it 6 electrons. Times 3 in the reduction gives it 6 electrons. And so what we end up with, 2 solid aluminums yields 2 aluminum ions plus 6 electrons. Draw a line and separate these. With the copper reaction, everything is times 3. Copper ions plus 6 electrons yields 3 solid coppers. And so now we're looking at it, this is still step 4. The electrons here equals electrons here. You have to have the same number of electrons in the reactants as the products. Final step, add the half reactions together. The common substances that show up on both sides can be canceled. So you could do this almost like a math equation, really. So everything on the reactant side we can put down here. 2 solid aluminums plus 3 copper 2 plus 6 electrons yields 3 solid coppers, 2 aluminum ions, and 6 electrons. We're almost done. The final step also tells us that if something appears in both the reactants and the products, they could cancel out. For instance, a lot of times this is water. You'll have water in the products, water in the reactants, cancel them out. As it applies to us right now, we have 6 electrons in the reactants, 6 in the products. They disappear. And so what we end up with is 2 solid aluminums plus 3 copper ions yields 3 copper solids, 2 aluminum ions. And if we were just looking at this original chemical equation, we would have walked away and said it was balanced. And in terms of atoms, it was. But we have to take into account the electrons.
This is taking what we learned 2 years ago.
What's that?
Taking what we learned 2 years ago, and then add an electron to balance it as well.
Yeah. Does anybody have any questions on this one before we move on? Or questions on the steps in general? Okay. So let's look at another one. This is the actual one from the front page. So we have solid copper plus nitric acid yields copper ions, 2 plus NO2 plus water. On the front, you'll notice I did not put water as a product. Looking at the front page, we were looking at observations and explaining those observations in terms of what we saw. Nitric acid started with a bunch of water, and when we make more water, it's really impossible to see it. That's why it shows up here, but not on the front page. Let's do oxidation numbers first. So go ahead and work on your oxidation numbers. And we'll come back and talk about it in just a minute. I think some of you are working ahead. That's fine. So we need to figure out what's oxidized. Losing electrons is oxidation. So copper going from 0 to +2 is losing electrons. The oxidation half reaction always has the electrons as the product. And then my reduction, nitrogen. So we have HNO3 yields NO2. Hopefully you're not working too far ahead based on a typo. And the reaction here has it listed as NO, nitrogen monoxide, NO2, nitrogen dioxide. Now I need to verify it because everything else might be screwed up too. Stand by for a minute. All right, so our example's all screwed up. Did everybody fix the NO and make NO2? Okay. So looking up here, now we're going to have to figure out what exactly happened with the electrons. So let's take a look here. Really, we're concerned with nitrogen. It went from +5 to +4. So what happened with this one? It gained an electron. Just one, right? So +1 electron, I'll just write E minus. Something else to consider, let's go down the steps. So write the reduction half reaction, good. Balance the half reactions. So we have an aqueous reaction. Balance the elements that are not hydrogen and oxygen. So we're good, that's just nitrogen. There's one nitrogen in the reactants, there's one nitrogen in the products. Number 2 says balance the oxygens with water. Well, we've got 3 oxygens, and here we've got 2, 3. So that one's fine. We don't have to add any water. Balance the hydrogens with H+. This is where we need one. We have HNO3, we have H2O. So we need one hydrogen on this side. So we added an H+. And it's aqueous, but we're out of room. Another thing about this hydrogen is that it balances out the charges. So you'll notice everything over here was neutral, and without this hydrogen, this side is not neutral. So, maybe beyond what we need right now. Make sure the electrons lost is equal to the electrons gained. What do I have to do? We're looking at 2 here and 1 here. We need to make sure that these are equal. So I'm going to multiply the nitrogen or the reduction half reaction times 2. So I've got 2H plus 2HNO3 plus 2 electrons yields 2 NO gas, NO2 gas, and 2 H2Os. And so this one we don't need, you don't have to mark it out, but now that we've got a new one, I just want us to understand which one it is. Now that the electrons are equal, we can add these two things together. So solid copper plus 2 hydrogen ions plus 2HNO3 aqueous. I'm not going to write the electrons down here. Let's go ahead and mark them out in the half reactions. Yields copper 2 plus aqueous plus 2 NO2 gas plus 2 H2O liquid. Cancel things that appear on both sides. That was just the electrons, and everything else looks good. My habit is just to verify that it's actually balanced. 1 copper to 4 hydrogens, 4 hydrogens, 2 nitrogens, 2 nitrogens, 6 oxygens, there's 4, there's 6. So this is a completed balanced redox reaction. Time to stop.